Yeah. Now the meeting is under recording. Okay. Good evening to one and all. So today we are going to discuss about the moving iron instruments. So yesterday we have gone through the moving coil instruments. So moving coil is nothing but we can make use of MC. We can call it as MC. PMMC, permanent magnet moving coil. So which is going to use for DC measurements only. Okay, because the direction of angle or the deflection or the current is directly proportional to the angle of deflection, where I is the angle, sorry, where I is the current flowing through the coil, and where theta is the angle of deflection. So always this I is directly proportional to theta. So if I increases, automatically theta also will get increase. So here, if you are making the current as negative, nothing but reverse direction of current, nothing but plus minus. Instead of that, if we go for minus and plus, then the current direction will be in the opposite. Then automatically the pointer will move in the negative direction. Okay, so that's why always we are using the moving coil instruments in the for DC circuits only, right? So now we'll go through the moving iron instruments. So in the moving iron instruments, according to the Coulomb's first law of magnetism, so unlike poles attract each other and the like poles repel each other. So we can see this animation. Okay. So from the animation, you can observe what's happening. So North Pole, and South Pole. If the two poles are same, so nothing but same poles. So in the bottom diag, or in the, let us go for the top diag, I mean first part. Okay, North South, South North. So if you are using like this, with the pole, the magnet is going to be gets attracted. Now if you are using North North, South South. Okay, so nothing but we can have the options as North South as well as South North. So attraction. Okay, North North, South South. So two magnets. So the first is for first magnet, second magnet, first magnet, second magnet, like that. So North North and South South will have repulsion. Okay, so here we are going to use both the case. So moving iron instruments are having two types. One is of attraction type, another is repulsion type. So we are having two types of moving iron instruments. One is attraction type, and second one is the repulsion type. Now observe this diagram. So here you can observe several things. Okay, so this is the portion where we can use for air friction damping. So why we are going for air friction damping? So dampings are nothing but oscillations. So in order to reduce the oscillations, we are going to use air friction damping. We are going to use air friction damping. So air friction damping is used in the moving iron instruments. Whereas in case of moving coil instruments, we have used eddy current damping. Okay, right. The pointer is there. The scale is there. Okay, the scale will be as of like this. And here you can observe, it is a just like a shape of like this. Okay, okay, this also of same magnitude, let us say. So the coil will be round as like this, nothing but along with this, the coil will be having more number of turns. That's why these dots we can observe, these dots are nothing but the coil. Okay, so the coil has been wounded as like this on this. So and this coil has been energized, and this coil has been energized, and here we are using a moving iron. Here we are using a moving iron. So this moving iron is going to attract it by the magnet, or repulsion from the magnet. So here moving iron we are using. Okay, this iron is going to get attracted Okay, so whether it is North Pole or South Pole, the iron will attract always. Keep in that mind. In the attraction type, now we are going to discuss about the attraction type moving iron instrument. So here, whatever the pole of the magnet, whether it is North Pole or South Pole, the magnet will attract the iron. So iron will be attracted by either the side of the magnet. So that's why we don't have any the pole variation or pole difference in that. Okay, along with the pointer, we can have the moving iron, the controlling weight will be there, and balancing weight will be there. So these are all the part of the system to provide or produce the controlling torque, right? So it consisting of a hollow or cylindrical or solenoid type of coil will be there. A spindle is sorry. A spindle is supported between the two jewel bearings and near to the coil. Okay, so the construction is almost similar to the what you can say the moving coil instrument. So jewel bearings are same. The oval shaped soft iron. So here we are using a oval shaped soft iron coil, moving iron. This iron is going to be used. Okay, this is going to be gets attracted to the uh, coil, energized coil. Okay. The pointer attached to the spindle. Now, the overall shape, the oval shape of the iron is freely movable in the inside the coil. So that is also one advantage why you are preferring oval shape. So the oval shape will have a smooth uh, movement in the coil. Okay, that is one advantage why you are going for oval shape. And the pointer moves on a graduated scale. So we'll discuss about what is graduated scale in the coming slides, because linear scale is different from the graduated scale. So why the graduated scale is used in MI instrument, that we'll discuss in the coming slides, right? The instrument is provided with a spring control. So spring control is going to use for the uh, controlling torque. So we can use spring control, or we can use what you can say gravity control, anything we can prefer, right? And the instrument is provided with the air friction damping. So these are all the basic requirements of the moving iron instrument as of the construction point of view, right? So when the current passes through the coil, when the current is passing through the coil, so here we are using the coil winding. So if the current is passing through this winding, then what will happen? This coil will energize. Nothing but this coil is acting as a magnet. This coil is acting as a magnet. Then nearby a moving iron is there. You can observe here. So a coil is energized, so it is acting as a magnet. Now the entire coil is acting as a magnet. Nearby the coil, the iron piece is there. So always this iron is going to be attracted by the coil. So when the current passing through the coil, uh, it magnetizes, and the coil attracts a soft iron piece inside the coil. So it is going to move now. Let us say now it is in this direction. Let us say it's a oval shaped direction of like this. Now it is moving inside. So the shape will becomes like this. It is going to turn. It is going to turn. Okay, because of this turning, along to the spindle, what we are using here, the pointer, okay, and the controlling weights, balancing weights, everything are connected, so that the pointer will move in the uh, it will have a deflection. So when it is going to deflect, automatically this air friction damping also will work accordingly. Okay, so these are all in a similar fashion. So when the spindle moves, all these are connected: the pointer, the controlling weight, the balancing weight, the air friction damping chamber. These are all connected to the spindle, so that all at a time, along with the pointer, these are also will move. So here, whatever the moving iron we are used, that iron is acting as a is attracted by the coil. Now the coil has been energized. The energized coil is acting as a magnet, and it attracts the iron piece or iron uh, or moving iron, what we can say. So it is iron. Now it is moving. So that's why we can call it as a moving iron, right? So as the iron is attracted to the spindle, spindle also will rotates. The pointer moves on the calibrated scale, which indicates the strength of the current flowing through the coil. So as the all the things are connected to the spindle, so automatically the spindle will move, will turn, or will deflect, so that it is going to have a deflection on the scale. Now, if the current reverses, now what? Now we'll discuss about a case. If the current reverses, what will happen? The coil, if the current reverses in the coil, it establishes the magnet is in the opposite direction. Okay. So what will happen? So the magnet may be north to south pole or instead of south to north pole. Let it be. Whatever it may be, it is having its own magnetic directions. So either from top to bottom or bottom to top, whatever it may be, the direction of current reverses, their magnetic lines also will change. So even though it is also acting as a magnet, so instead of let us say this is a magnet, let us say north pole and south pole, as it is a coil, let us say. Okay. Now as the current reverses, then this becomes south pole and this becomes north pole. So even though it is north pole and south pole, in this case, it is again acting as a magnet. This magnet is going to attract this iron piece. So again, this iron is going to deflect or nothing but rotate. So even though you are reversing the direction of current, it is going to establish the same magnetism property in the opposite direction. So again, it is acting as a magnet. This magnet is attracting the iron. So iron will start deflecting. Once it is deflecting, it is connected with the spindle. The pointer will move. The balance and control weights also will move, and air friction damping chamber, in that also damping process is also going to take place, right? So with that, what we can have a conclusion here, if you are using a moving iron instrument, so when you will get a reverse direction of currents. So if you observe let us say this is the x-axis, time, with respect to time, and the magnitude, this is the DC current or DC voltage, what we can say. So every time we are discussing about the current, if it is an alternating current, what we'll have one positive half cycle, one negative half cycle. So here in the positive half cycle, we can have positive currents. In the negative half cycle, we can have negative currents. So here always in the DC, always positive. In the case of AC, we can have positive for half cycle and negative for the remaining half cycle. So current will reverses in the alternating currents. Okay, even if you are reversing this DC current, what will happen? This DC current will have a negative value. We can have, let us say, so this is x-axis time. Now we'll have minus value. Okay, so negative, even though it is negative, we can have magnetic property. So moving iron is going to be, that iron piece is going to be attracted to the coil, right? So whatever we are using, the magnet is attracting the, whatever the direction of the current, the magnet is attracting the iron piece, so that we can have always deflection. So we can have a conclusion here. The deflection torque remains same. Even though the direction of current reverses, we can have the deflection torque will be in the positive. So that we can have a positive deflection, nothing but a clockwise deflection we can have. We can have a clockwise deflection, right? So therefore, we can use this instrument for both AC as well as DC. Now, at different instances, we can see at final deflection position, what will happen? At final deflection position, what will happen? So deflection torque should be equal to controlling torque. We have already gone through. So nothing but TD should be equal to TC. Now we should know, we already know that what is TC. TC equal to K into theta, where K is the spring constant and theta is the angle of deflection. So this is fixed. Now we need to find out what is TD. TD is nothing but the deflection torque. The deflection torque, how much amount of deflection torque is being produced in case of moving iron instrument, that we need to derive. Okay. Okay, as we said, this TD equal to TC. Therefore, the scale is stable, right? The scale is non-uniform because of the air friction damping. Of course, this we will discuss later about the non-uniform scale. The scale is cramped. Why it is cramped? Cramped means non-uniform or compressed. We can call the cramped as compressed scale. Okay. Why? That reason that we will see in the coming slides, right? After deriving the deflection torque expression, we can we will get what is cramping scale or what is non-uniform scale, right? And whatever the voltages or currents, whatever we are measuring, so always in terms of RMS, okay, root mean square. See, observe these various conditions. So TD, the first one, the deflection torque. TD is the deflection torque. Theta is the angle of deflection. L is in the coil, inductance coil, okay, or the inductance of the coil, okay, in terms of henries. And I is the initial current, and DI. So DI is nothing but change in current. DI is nothing but change in current, and DL change in inductance. L stands for inductance, right? Theta, D theta, change in angle of deflection. So I will be there, L will be there, theta will be there. So current, inductance, and angle of deflection. Now we can observe the change. So because as the input increases, there is a change in current, nothing but the current will increase. Di becomes Di, L becomes DL, and theta becomes D theta. So nothing but we can have one expression, E equal to D by dt of L into I. Okay. So still the students are joining. Right. Okay. So E equal to the amount of voltage. So E equal to d by dt of Li. So we can have the UV principle. Okay, d by dt of UV, U dV plus V du. Nothing but like that we can have the formula here. So d by dt of Li equal to L into di by dt and I into dl by dt. So we can have this expression from the UV rule. Now the energy consumed by the meter. Now we are discussing about the energy. So voltage into current will have energy. Voltage into current into time. Okay, energy means voltage into current into time. So here capital E stands for, here the capital E stands for the energy, where small e is nothing but the voltage, I is nothing but the current, and dt within the time how much amount of energy has been consumed. So EIDT is nothing but the energy consumed by the meter. Energy consumed by the meter. That's what we are calculating this value. Now multiply these things. So we know that what is in the previous expression, E equal to L di by dt into I dt. Nothing but we are multiplying this voltage with I dt term. So L di by dt into I dt plus I into dl by dt into I dt. So we are just multiplying with I dt. So voltage we have already expressed. That voltage is multiplied with the current and the time. So I into dt and I into dt are added, sorry, are multiplied with the with this expression. So whatever the expression here we are seeing, E equal to L di by dt plus I dl by dt, right? Now we are just multiplying. So here we can get Li into di. Okay, this dt will get cancelled. Here also dt and dt will get cancelled. So L into I, Li into di. So Li di is the first part, and here I multiplied with another I. So becomes I square into dl. So Li dl di plus I square dl. So this is the first expression what we can have, the energy. Now for this is the amount of energy required to move for theta angle. Now if you are increasing the current value, then what will happen? The current will increase. Initially it is I, now we are increasing to di. So for a small increment in the current, that's what we are saying, for a small increment in current di, the deflection is increased by d theta. Is it correct or not? Yes, we are going to increase the deflection. As let it be, initially we are measuring at 10 volts. So the pointer will give or will make a display at 10 volts on the scale. Now I am increasing to 15. Then what will happen? The amount of current flowing through the coil will get increased. Hence, the current flowing the angle of deflection also will get increased, so that theta will increase. Now the pointer will deflect by certain angle to get 15 volts on the scale, right? Similarly here also, here the current increases, so that the d theta also will get increased. Now the energy stored by the inductor in the inductor of the meter. So in the meter we are having the coil. Coil is nothing but the inductance. So coil is nothing but the inductance. So here what we can have, excuse me. Right. The coil is nothing but the inductance. So how much amount of energy is being stored in the inductor? So that is a general regular expression, half Li square, half into L into I square. So that is the amount of energy stored in the inductance in the form of magnetic field. Keep in that mind. Now the new energy storage due to the increment of the current. So already we have calculated uh, how much amount of energy is being stored. Now what we are doing, whatever the amount of energy stored in the meter has been increased by sudden because of the current increase. So now the new energy, now we are saying about new energy. So new energy storage due to the increment of the current. Now the current has been increased by dl. So L into I square here. L into dl nothing but as the inductance also will get increased, then the current also will get increased. So half into, instead of L we are using dl plus dl. So dl is the variation and L is the initial value. Okay, I is the initial current and di is the change in current. So the same expression half Li square will becomes as new value half L, instead of L we are writing L plus dl into I plus di whole square. Right, just simply we are substituting in place of L plus dl, in place of I plus di. Of course square is there as usual. Now the change in stored energy. So change in stored energy means this is the energy which we have obtained because of increase in current and inductance value. Change annappudu, then what we can say, whenever we are calling change, this is the new energy and this is the old energy. So new minus old. So new energy minus old energy. So it gives minus symbol. So what is the new energy minus the old energy? Half Li is nothing but the actual energy stored in the inductance coil. Okay, because of the increasing in the current, there is increase in inductance, so that there is increase in current. So L plus dl, I plus di. Okay, now we are expanding this expression. Now L plus dl as usual, like that only I placed I plus di whole square, just like a plus b whole square. So a square plus b square plus 2ab. So I square plus di square. Sorry, here this is a bracket has been missed. Di square. Okay, right. 2 into I into di. Okay, so a square plus b square plus 2ab, like that. Minus, okay, change na, minus half Li square. Now what we are obtaining again, L plus dl into I square plus 2il 2idi plus di square. So again we are multiplying. So L into I square. So half into L into I square. Half Li square. Half into L into what you can say, 2idi. So half and 2 will get cancelled. So Li di. Then again half into di square. So half into L into di square. Okay. Again, next with the dl we are multiplying. Half into dl into I square. Next term. Again half into, so half and 2 will get cancelled. I into dl into di. Half into dl into, like that we can have all the terms. So here minus again the old energy stored in the meter, sorry, in the inductance coil. So this and this will get cancelled. Okay, first part of Li square and the last term minus half Li square will get cancelled. Plus and minus will get cancelled. Now here we can have IL values we can consider. Di di is nothing but a small change. If you multiply small change, nothing but square of the small change becomes again small. So I have already given the example. Anyhow, once again I will give. Let us go for 0.2. So 0.2, if you square it, what will happen? 0.2 into 0.2. Okay. 0.2 square, nothing but 0.2 into 0.2, which is nothing but 0.04, which is less than 0.2. Keep in that mind. So the squared value will be lesser than the actual value. Let us say 0.9 square, that equal to 0.9 into 0.9, that equal to 0.81. So where 0.81 is less than 0.9. Okay, let us go for 1. 1 into 1 becomes 1. Of course, there is no change. Let us go for 1.1 into 1.1. That equal to 1.21, where 1.21 is more than 1.1. So less than, if you are having lesser value, di is nothing but the lesser value. These lesser value, even if you square it, we are going to get much more lesser value. So that's why we are going to neglect the di square terms, dl into di or di square or dl square, like this, right? So after neglecting all these things and simplifying, the remaining terms what we are going to obtain is l I di, one term, and half l square, sorry, I square into dl. These are only the two terms will be available, nothing but neglecting second and third order differential terms. Okay, so that we are getting only these terms, li dl plus half I square dl. So these are only the terms what we can have. So work done. So td into d theta, td into d theta. So here we are going to get the value of the deflection torque. So from this expression, the law of conservation of energy, we can have the energy consumed equal to work done plus the change in stored energy. So how much amount of work has been done as an output? So here work done means deflection made by the pointer, deflection made by the pointer, and stored energy means how much amount of energy is being stored in the coil. So these two things we need to add for the total energy consumed. So we are substituting these expressions. We are going to get, so Li into di plus I square into dl, that equal to Td into d theta plus, this is the what you can say, deflection torque, and then this is the stored energy. So the total value we can calculate as like this, and we can simplify. So this term and this term will get cancelled, and td d theta equal to half I square dl. So this is the expression what we can have. So from that expression we can have d theta or td equal to half I square dl by d theta, of I square dl by d theta. You can observe L is the inductance of the coil, which is of course fixed, and d theta, which is also, I mean, a variable term, let it be. And here we can observe Td is proportional to I square. We can have that expression. Keep in that mind. Now from this we can say the deflection torque is produced is proportional to the square of the current. So Td is proportional to I square. Td is proportional to I square. For AC measurement, nothing but alternating current measurements, the readings obtained will be in the RMS value of the current as well as the voltage. So due to the square law response, the instrument scale of the moving iron is non-uniform. That's what I said. So if you are observing 0.9 into 0.9, let us say 0.9 amps of current is flowing in the coil. Now we are multiplying the square, I square. So 0.9 square, that equal to 0.9 square equal to 0.81. So where 0.81, actually we need to measure 0.9 amps, but what it is showing 0.81 only. So instead of showing 0.9, it is showing 0.81 only. So it is deflecting with a lesser value. So we don't have that much what you can say, deflection angle. So that's why initially we are using a compressed scale or cramped scale, or else we can call it as a non-uniform scale. Okay, so that is the reason why we are using a non-uniform scale in case of moving iron instruments, right? Now we can have the various what you can say advantages. So they are cheap, robust, reasonable accuracy. So accuracy is we are seeing as reasonable means we are having certain drawbacks while discussing that we'll get in detail. Simple in operation, of course. Operation is very simple because the magnet we are using as electromagnet and the moving iron you are using. So attraction or repulsion, whatever it may be, it is a simple operation. So simple in construction, high operating torque can be produced. So TD is proportional to square of the current. So high torque will be produced. Okay, and momentarily overload capacity. So even at the overload capacity, it can handle and use for both AC and DC. So we can use these MI instruments for AC measurement as well as DC measurements. And few of the disadvantages also there. So non-uniform scale, as we already said. See, observe this here. So 0 to 50, we can have a compressed scale. So what is the distance between here 0 to 50 is very short. And observe this from 50 to 100, this distance is more. Again 100 to 150 like this, and 150 to 200 like this. So whatever the meter you can see, 0 to 0.5 compress. I mean at the lower ends we can have compressed scales. Even in this case, okay, at the lower measurements, we can have compressed scale. The power consumption is more, as we said. The inductance coil or the coil will store certain amount of energy, so that the power consumption is also increased. And errors are introduced due to the hysteresis and stray magnetic fields. We are using the iron piece, so it is having certain magnetic properties. So hysteresis errors will be introduced, and we are using a electromagnet. So nearby, if any other magnetic fields are there, nothing but we can have a stray magnetic fields. So because of these stray magnetic fields, there are errors are going to be gets introduced. And errors are also introduced due to the change of frequency in case of AC supply. So when we are using for AC measurement, if the frequency changes, you might have know about the hysteresis loss formula. It is proportional to certain frequency terms. So that's why the errors whatever introduced in moving iron instruments while measuring AC supply. So because of change in frequency, there is a change of, or there is a chance of introducing the errors, right? And now we can use this MI instrument as a voltmeter as well as ammeter. Okay, when the instrument is connected across the supply, let's keep in that mind. Whenever you are using this meter, voltmeter, we should connect across, nothing but here plus minus or phase neutral. So whatever we are using, either plus minus or phase neutral, we are going to get right.
Yeah.
So when the instrument is connected across the supply, the current is proportional to the voltage flowing through the coil, and the flux produced inside the coil attracts the oval shaped moving iron, so that the deflection will takes place. So as a result, the moving vein moves inside the coil, so that the pointer will have a deflection. Will have a deflection on the scale. Similarly, we can have ammeter. Okay, so here we are using either DC or AC, whatever it may be the supply, and here we are going to use in series with the supply or in series with the load. Okay, so in a series circuit, we are going to use this ammeter. Ammeter should be always connected in series. Okay, so the flux produced inside the coil attracts the oval shaped moving iron. Same in case of voltmeter. Here also in case of ammeter. Now coming to the repulsion type. So what is the repulsion? So as we have already gone through the attraction and repulsion, if we are using what you can say North Pole and South Pole, we can have attraction. We can have attraction, either north south or south north, nothing but opposite poles. If same poles are there, nothing but uniform poles, north north, south south. In this case, repulsion will take place. In this case, repulsion will take place. So based on this principle, earlier what we have seen, we have observed about attraction. So if it is attracted, then how about the pointer will deflect? Now here we are discussing about repulsion. If it is repelled, nothing but repelled with each other, then how about this? Right, I'm getting a call just. Right. So now we are going to discuss how a repulsion will takes place in case of moving iron instruments. Right. So parts of moving iron instruments, of course, we will see the parts: air chamber for what you can say damping torque, moving vane, nothing but the pointer, the alnico core, so nothing but the metal former. On this metal former, we are going to make the winding. Okay, so mum metal or alnico core we can use for manufacturing the things, and pointer, coil, jewel bearing, scale, mirror, and fixed iron vane. So these are the things what we are going to use in case of repulsion type of moving iron instrument. So in the attraction type moving iron instrument, we have seen a oval shaped moving iron. We have seen is a oval shaped. But whereas in case of repulsion type, we are going to see a strip type. Strip type. So metal strip, just like a metal strip. Okay. Now we will see the diagram. Observe this diagram. These two diagrams you observe. Okay. See, in the right diagram, in the right side diagram, we can observe this is the spindle, of course. So to the spindle, if you come down, so if you observe, this is the portion where I am highlighting. Okay. So that's just a plate. It's just like a plate or strip. So that strip has been attached, nothing but just like this. So it is a spindle. You can see in the screen, it is a spindle. To the spindle, that metal strip has been attached. Okay. So as this metal strip moves, as the spindle moves, automatically the metal strip also will move. So that you can observe here. So just I will remove this. See. So this metal strip is having north south poles. Okay, north south poles means it is also acting as a magnet. So this metal strip is also going to be energized along with the coil. So this is the winding coil. Okay, this is the winding coil. So electromagnet. So it produces the magnetic flux, and whatever the coil we are using, whatever the quantity we are going to measure, that measured quantity is that current is passing through this metal strip. Nothing but this is also acting as a magnet. Now here you can observe north north. You can observe here north north, and you can observe here south south. So north north at the top of the metal strip, and south south at the top of the metal strip, at the bottom of the metal strip, or nearby. So what will happen if the two north and north poles are coming nearby? Automatically it will repel. Similarly, at the bottom, we can observe south and south. At the bottom, we can see south and south. So again, it is repel. So north, south on the top and bottom of the metal strip, and north and south on the coil. Okay, moving iron coil. So here, north and north, so nothing but on the metal strip we can see. We can have just once again. I will. How to zoom this? Just wait. I will show you clearly. Yeah. So up to a certain extent, I can zoom. Right. Here you can observe the north and north. Are you able to see the cursor? Or I will go for the pointer. Yeah. So while zooming, the pointer may not work. I think so. Okay. Anyhow, at the top, you can observe the north and north. Okay. The mouse movement, what I am doing. At the bottom, we can have south and south. So to the spindle, the metal strip has been attached. The metal strip has been attached, and here we can have the coil. So we can have the coil. So to this coil, again, as the current is passing through the coil, it produces the north and south poles, obviously. So these north and south poles of the coil and the north and south poles of the metal strip, okay, are going to be at one place. So north and north will get repel, and south will get repel. So with this rippling principle, now we can see, I can highlight the point. So north and north, south and south. Just to the spindle, to this spindle, this metal strip has been attached. So earlier we have used a ring, but moving iron ring in a oval shape ring. Now we are using it as a plate. Okay, so that is the difference between these two, right? And we can have various parts in the left side diagram. You can observe left side diagram. You can observe about the various parts, zero adjustment, damping winding, or damping magnets are there, field coil, and spring bearings, screws, spiral springs, okay, movable iron core, fixed iron core, bearing point, etc. etc. These are all the internal construction. Okay, in the examination point of view, we can draw the second diagram. That's enough for repulsion type of moving iron instrument. Now, I hope it is clear to you. Now, coming to the construction point of view, it consisting of a fixed hollow cylindrical coil, and then inside the coil, two soft iron rods or vanes are parallel to each other and parallel to axis are placed, so that it forms like a, what you can have, a metal strip. One iron rod or vane is fixed to the coil, and another rod is fixed to the spindle, so that the both will come near and apart. So if they come near, north north, south south will be there, then again it will start repelling each other. Okay, as the point ratchet to the spindle, so the spindle is free to rotate in the inside the coil. When the uh, here we can use the spring control, and air friction is also going to provide for reducing the damping. Okay, and when current flowing through the coil is zero, The pointer is at initial position and it is also representing zero deflection. Okay, then the fixed and moving irons are close to each other by the time because there is no current flowing through the coil. Okay, now once the current increases, when the operating current passing through the coil, but the current increases, it produces the magnetic field. Okay, the two vanes within the coil are magnetized similarly with same polarities. Okay, so with same polarity means north north and south south will be observed here. So as north and north, south and south will be there, then they are going to repel each other. Hence, the two magnets will repel each other. So movable vane mounted on the spindle moves away from the fixed iron so that we can have connected to the pointer, etc., so that we will have a deflection. So the moment of the moving iron depends on the strength of the current through the moving coil. You can observe a small magnet can attract up to a certain extent. If a large magnet can attract much more effectively, you might have experience while playing with the magnets. Okay, a small magnet, if it is trying to attract a iron piece, okay, we will have a certain distance between the two magnet and the iron. If the magnet size increases, even for the longer distances also it will attract nothing but it produces more amount of strength. Okay, nothing but here how we will get the magnetic property by flowing the or by sending the current through the coil, right? So the pointer move on a graduated scale as already discussed. So graduated scale is required here, and thus the current flowing through the coil can be read directly on the scale. And we are several advantages also there. It is cheap and minimum maintenance is required and simple in operation, robust construction, and used AC as well as DC, as we have already discussed in case of what you can say attraction type of moving iron instrument. Then reasonable accuracy. So accuracy in that case, we can have not exact accuracy, a reasonable accuracy what we can have. And disadvantage, scales are not uniform. As I have already said, it is having a cramped scale or compressed scale. Then the power consumption is the power consumption at low voltage is high because it is going to store certain amount of energy in the coil. The stiffness of the spring decreases with the increase in temperature. So we are using a spring control. That spring stiffness is going to be changes by change in temperatures. Hysteresis in the iron of the operating system and stray magnetic field causes the errors. So we are using the iron. Iron is having certain amount of hysteresis losses. So it introduces these losses. These losses will cause the errors, and stray magnetic field also causes the errors for reading. And change in frequency, as I already said, change in frequency. Hysteresis are related with the frequency terms. As the frequency changes, we'll have changes in the errors. So similarly, moving iron instrument type of voltmeter, how we are going to connect and how the flux is being produced in the coil and how we are going to get the deflection on the scale. So as voltmeter as well as ammeter. A similar case, what we have discussed in case of moving coil, attraction type of meter. Now, the same deflection torque what we have seen, same in this case of repulsion type of moving iron instrument also. Same expression we can have. See, the energy stored E equal to d phi by dt, nothing but the voltage here we can say. Okay, d phi by dt. So d into phi is nothing but L into I. So we can have I into dl by dt plus L into di by dt, that expression. And the stored energy, electrical energy, E into I into T. So voltage into current into time. The same expressions here also we can use. So if you are asking for calculate the deflection torque in case of traction type of moving iron instrument or repulsion type of moving iron instrument, the expressions are same. So final expressions will be Td equal to half into I square into dl by d theta. So these expressions are same in case of attraction type or repulsion type of uh, moving iron instruments, right? As we know, the controlling torque is case Tc equal to k theta. K is the spring constant and theta is the deflection in terms of radians. So at the final deflection position, we can have controlling torque is equal to the deflection torque. So K theta equal to K theta is nothing but TC. TC equal to TD. So TD equal to nothing but half into I square into DL by D theta, right? So deflection from that deflection equal to half I square by K into DL by D theta. So we can have the angle of deflection. Here you can observe theta is proportional to I square. Here theta is proportional to I square. That's what we can have. So earlier we said TD is proportional to I square. Now we are saying theta is proportional to square of the current. So as the current squared, according to that, the angle of deflection will change. Okay. Advantages: robust construction, relatively cheap, suitable for measurement of both AC and DC, can withstand overload. And disadvantages: as a deflection is proportional to square of the current, hence the scale of the instrument is non-uniform. Okay, compressed scale or cramped scale, and it is going to affected by the stray magnetic fields. Hysteresis errors will be there. So in order to reduce the hysteresis error, we can make use of nickel iron alloy for manufacturing of the vanes as well as the coil, iron frames. And read errors in the moving iron instruments. Why you are saying read errors means the scale is compressed at the start from 0 to certain value. We will have a compressed scale. By that time, it is difficult to take the reading. So that is the read errors can take place while using the MI instruments. So variation of frequency, as I already said. Okay, as the increase in frequency, iron losses will increase, and coil impedance also will get increased. So power consumption, I square or losses also will get increased. Nothing but certain amount of energy will be stored in the form of magnetic field. Now we can have the comparison between MC and MI. Okay, moving coil and moving iron. So in various issues we can have. So how about the deflection torque? How about the deflection torque to the current value, damping torque, controlling torque, uh, and scale, construction point of view, power consumption point of view, the application point of view, and usage. So these are all the various factors where we are going to compare the moving coil instruments as well as moving iron instruments. Now you can see deflection torque as the coil moves in the magnetic field. So in the moving coil instrument, we are used the moving coil is used, but whereas in case of moving iron instrument, soft iron is moved in the magnetic field. And deflection torque is proportional to the current. TD is proportional to the current in case of MC, and TD is proportional to square of the current. TD is proportional to square of the current. So here TD is proportional to I, and here TD is proportional to I square. I square. Okay, and damping torque is provided by eddy current damping in case of MC, and air friction damping is provided in case of MI. And spring controlled instrument for MC meters, and gravity control can be used for MI instruments. And control torque is proportional to angle of deflection. Nothing but TC is proportional to theta. And whereas here angle of deflection is in terms of sine angle. So nothing but instantaneous values like that we can say. So we can have uniform scale in case of MC and non-uniform scale. And construction is delicate and sensitive. MC meters are delicate as well as sensitive, and whereas MI instruments are robust and reasonably accurate. And power consumed by the MC meters are low, and higher power is going to consumed by the moving coil instruments. Applications: moving coil is used in DC circuits, and moving iron will be used both in AC as well as in DC. And meter can be used for voltmeter, ammeter, and galvanometer in case of MC, and ammeter, voltmeter, and wattmeter in case of MI. So this is about moving iron instruments. Okay, now the time for queries. So whatever the doubts you can have, you can make it. You can send the message in the chat box. So around 60 students have joined. So few of E2 students also asked me, sir, can we join? Okay, if you are interested, you can join. I don't have any objection. So up to 500 members, we can join in this. Okay, do you have any doubts? Is it clear? Any doubts? Okay, if you don't have any doubts, then I can leave the meeting. Is it clear? Can anyone respond in the chat box?
Okay, sir.
Okay. By tomorrow morning, I will send the uh, video link to you once again. So whatever the meeting, whatever the class we have completed right now, it will take around a half day, around 6 to 7 hours to convert into uh, MP4 format, so that you can download from the Google link, right? You can view, you can download. Now I am stopping this recording.